Alright, everybody, as you are coming back from break and had a chance to stretch, we're going to pick back up with minute ventilation. Minute ventilation, also known as minute volume, is the amount of air that is moved in and out of the lungs in 1 minute. This is determined by multiplying the tidal volume by the frequency of ventilation within a minute. The tidal volume is the volume of air breathed in with breathed in with each individual breath. The frequency of ventilation is generally calculated as the number of ventilations in 1 minute. The formula being tidal volume times frequency of ventilations equals your minute ventilation. An average sized adult has an average tidal volume of about 500 milliliters and approximately 12 breaths per minute. Thus, based off of the formula that we've just discussed, the minute ventilation will be calculated as what? Right, 500 times 12, which equals what? Right, 6,000 milliliters or 6 liters per minute. So with a tidal volume of 200 milliliters and a ventilatory rate of 28 per minute, it would appear as if the minute ventilation is near the normal of 6,000. However, even though the minute ventilation appears to be near normal in this patient example, severe hypoxia may still occur in this patient because of a small amount of air actually getting to the alveoli for gas exchange. Increasing the frequency of ventilation may improve the amount of air moved in and out of the respiratory tract within a minute. However, if the tidal volume is too low, an adequate amount of air may never make it completely down to the alveoli for gas exchange, but will actually instead remain within the trachea and the major bronchi. Alveolar ventilation, this is the amount of air moved in and out of the alveoli within 1 minute. So as we breathe in, air goes down our trachea, goes into our bronchi, goes to the bronchioles, which bronchioles then terminate in the alveoli. So alveolar ventilation is the amount of air moved in and out of the alveoli in a minute. The key in this definition is specifically the amount of air moving in and out of the alveoli, unlike minute ventilation, where the calculation is concerned only with air movement in and out of the respiratory tract and lungs. Alveolar ventilation is related to the concept of anatomic dead airspace. Dead airspace consists of anatomic areas in the respiratory tract where air collects during inhalation, areas where no gas exchange is going to occur. Thus, a reduction in tidal volume may dramatically reduce the alveolar ventilation, even when the patient increases the frequency of ventilation to compensate. Because when you take that breath, the alveolar space is actually the last space to get any air in. So if you increase your respiratory rate and decrease your tidal volume, that's why you're going to be you're breathing in the same amount of air within a minute, but you're getting less air down within the alveoli itself. A low tidal volume decreases the alveolar ventilation by not putting enough air into the alveoli with each breath. A ventilatory rate that is too slow will not provide enough air in the alveoli for adequate gas exchange. A ventilatory rate that is too fast can cause two problems. One being, the rate is so fast that it does not allow the lungs adequate time between breaths to fill, thus reducing the tidal volume. Or two, a fast rate would require a large amount of energy and muscular workload that may not be able to be sustained, thus setting the patient up for respiratory failure. Ventilatory rates of 40 per minute or greater in an adult patient and greater than 60 within a pediatric patient are too fast to be sustainable or to allow adequate time for a normal tidal volume. And generally speaking, whenever an illness or injury affects the lungs, it typically causes a change in the tidal volume, which thus causes a reflexive increase in the respiratory rate. For example, severe pneumonia can cause the alveoli to become plugged with pus. This thus causes a reduction in tidal volume, and hypoxia then results. A pneumothorax collapses a lung and makes it difficult for the alveoli to inflate. This thus causes a drop within your tidal volume. If a patient has a flail segment, the bellows action of the chest is lost and they cannot entrain as much air. And this can then cause a drop in alveolar ventilation and hence cause a drop in tidal volume. Breathing is mostly an involuntary process that is controlled by the autonomic nervous system to maintain normal gas exchange. Receptors within the body constantly measure the amount of oxygen, carbon dioxide, and hydrogen ions and send signals to the brain to adjust the rate and depth of respiration. You do have some voluntary control over your breathing that allows you to hold your breath and alter your breathing pattern during talking, laughing, and singing. However, when you get to the point that your body is deprived for oxygen, such as holding your breath, your body then takes back over control and makes you breathe again. Primary involuntary control is through the respiratory center located within your brainstem, which sends out stimulatory impulses to the respiratory muscles. The central chemoreceptors are located near the respiratory center in your medulla. These receptors are the most sensitive to carbon dioxide and changes within your pH of the cerebrospinal fluid, or CSF. The pH is a measurement of hydrogen ion concentration. The peripheral chemoreceptors are located within the aortic arch and the carotid bodies in the neck. These chemoreceptors are also somewhat sensitive to CO2 and pH, but are most sensitive to the level of oxygen on the arterial blood. As the level of oxygen within the blood decreases, the peripheral chemoreceptors signal the respiratory center in the brainstem to thus increase the rate and depth of respiration. Thus you can have something called the hypercapnic drive. This is what we normally breathe in, where control of breathing is regulated by the level of carbon dioxide in the blood. In an abnormal respiratory person, such as someone with COPD, is subject to have something called the hypoxic drive, where control of breathing is regulated by the level of oxygen in the blood due to failure of the central chemoreceptors. Okay? So in a normal person, our breathing is controlled by the level of carbon dioxide in the blood. During the hypoxic drive and the abnormal drive, it is based off of the level of oxygen in the blood due to failure of the central chemoreceptors. Patients with COPD or chronic obstructive pulmonary disease, such as emphysema, tend to retain carbon dioxide in arterial blood as a result of the lung disease causing poor gas exchange. When the arterial CO2 level is chronically elevated, the central chemoreceptors become insensitive to the small changes that typically stimulate ventilation. The peripheral chemoreceptors then become the primary stimulus for ventilation. Instead of a small increase in carbon dioxide levels being a stronger stimulus for ventilation, the peripheral chemoreceptors rely on a decrease in the oxygen level to stimulate ventilation. Thus, hypoxia becomes the stimulus for ventilation in place of hypercarbia, hence the hypoxic drive. Within our lungs, there are three types of receptors that help provide impulses to help regulate respiration. The first one being irritant receptors. These are found within your airways, such as in your nose and in your trachea. These receptors are sensitive to irritating gases, aerosols, and particles that are in the air. When these are stimulated, when these are set off, they cause you to begin coughing, may cause bronchoconstriction, and increase the ventilatory rate to try to force it out of the airways. Stretch receptors are found in the smooth muscle of your airways. And what these do is when you take a breath, they help ensure that you don't overinflate the lungs. So when they sense that the lungs are getting too big, they send a signal back up to the brain to say, stop taking a breath and exhale. J receptors, these are found in the capillaries that surround the alveoli. These are sensitive to increases in capillary pressure. When they become activated, they stimulate rapid and shallow ventilation to help decrease the amount of pressure around the alveoli. There are three respiratory control centers that are contained within the brainstem: the dorsal ventilatory group, or DRG, the ventral respiratory group, or VRG, and the pontine respiratory center. The ventral respiratory group and dorsal respiratory group are located within the medulla oblongata in an area referred to as the medullary respiratory center. The pontine respiratory center, also referred to as the pneumotaxic center, is located in the pons of the brainstem. These centers receive sensory input and transmit impulses to the skeletal muscles, controlling ventilation, thus causing them to either contract or relax depending on what the impulse is. The ventral respiratory group, it also assists in the control of our basic pattern of breathing. It also contains inspiratory and expiratory neurons. The dorsal respiratory group also receives sensory input and communicates it to the VRG just for further input on the rate and depth of breathing. The pontine respiratory group, it sends inhibitory impulses to the inspiratory neurons of the VRG to turn off inhalation and ensures that we're able to have a smooth transition between inhalation and exhalation. So that way there's no issues when we're taking our breath. The ventilation and perfusion ratio. This describes the dynamic relationship between the amount of ventilation the alveoli receives and the amount of perfusion through the capillaries surrounding the alveoli. This relationship determines the quality of gas exchange across the alveolar capillary membrane, which influences the amount of oxygen entering the blood and the amount of carbon dioxide exiting the blood. The dynamic relationship between ventilation and perfusion in the lungs can be used to explain the etiology or causes of hypoxemia or inadequate oxygen concentrations in the blood. So when you take a breath, you have your external air coming in. You have CO2 crossing that membrane into the alveoli, O2 coming across to get into the bloodstream to then be flowed through. It then goes through the systemic circulatory system, where once it gets to the body cells, oxygen then crosses that membrane to get into the cell, while the CO2 and the other wastes from the cells through aerobic metabolism, hopefully, then crosses that membrane again to then go back into systemic circulation to come back to the lungs, and then be exhaled through respirations. In the ideal lung, each alveolus would receive an adequate amount of ventilation and a matching amount of blood flow through the surrounding capillary, thus resulting in a VQ ratio that is equal. This ideal condition never exists because of the effects of gravity on blood flow, the structure of the lungs, and shunting of blood. With an individual in a standing position, gravity pulls the lungs downward towards the diaphragm, compressing the lower lobes. As the lower lobes are compressed and blood is pulled down to the bases of the lungs, air then travels upwards to the apex or top of the lungs and increases the residual volume. Interestingly though, the alveoli in the apexes of the lungs have a greater residual volume of air. They're larger and have a higher surface tension, but they are fewer in number compared to other areas of the lungs. These larger alveoli in the apex have a higher surface tension, which makes them less compliant and harder to inflate during ventilation. Thus, the tidal volume is shifted to the lower lobes, where the lung is more compliant and there is less surface tension. Because gravity pulls the blood downward, less pressure is required to perfuse the lower lobes of the lungs compared to the apexes. As a result, the bases of the lungs receive a greater amount of blood and are much better perfused than the apexes. This is a desirable condition because the greatest amount of ventilation also exists in the base of the lungs. The ventilation-perfusion ratio is never at an ideal state in any zones of the lungs. Within the apex, the amount of available ventilation in the alveoli exceeds the amount of perfusion through the pulmonary capillaries. That is, there is more oxygen available within the alveoli than the supply of blood can pick up and transport. This is wasted ventilation. In the bases, the amount of perfusion exceeds the amount of ventilation. This means there's more blood moving through the pulmonary capillaries than there is alveolar oxygen available for it to pick up, thus causing a waste in perfusion. Overall, under normal conditions, how you are breathing right now, right this very second, perfusion exceeds the amount of available ventilation. The ventilation-perfusion ratio is the match between the amount of air entering the alveoli and amount of blood circulating to the alveoli for gas exchange. A ventilation-perfusion mismatch leads to decreased gas exchange between the alveoli and alveolar capillaries. So thus, when you have blood flow coming through here and you have perfusion without a ventilation, none of this blood is able to be properly oxygenated, hence why it's blue. Blue is deoxygenated. When you have ventilation without perfusion, so you have a clot somewhere before the alveoli, I'm breathing in, I'm getting air in, but I'm getting no blood flow. And ideally, there should be a constant flow going around. The perfusion of blood to the pulmonary capillaries is affected by the amount of air and pressure inside the alveoli and the pressure of the blood flowing through the capillary bed. If the pressure in an alveolus exceeds the blood pressure in the capillary bed, blood flow through the capillary stops. This is most likely to occur in the apexes of the lungs, where the pressure inside the alveoli is highest and the blood flow is lowest. However, it may also occur in the patient who is losing blood from an injury, thus having a decrease in blood pressure. A disturbance on the ventilation side of the ventilation-perfusion ratio can lead to hypoxia. If a condition or injury causes less oxygenated air to be available in the alveoli for the amount of blood flowing through the pulmonary capillaries, the end result will be less oxygen saturating the blood and less oxygen delivered to the cells, creating hypoxemia and cellular hypoxia. In this condition, there's a wasted perfusion because the blood is available, but there is an adequate amount of oxygen to be picked up. Thus, our management goals should be aimed towards improving alveolar ventilation, be that by relieving bronchoconstriction, airway occlusion, or supplementing ventilation in the patient with respiratory failure. A perfusion disturbance can also lead to severe cellular hypoxia. If a patient has lost a substantial amount of blood, or if the right ventricle is unable to adequately perfuse the lungs, then it will create a situation of wasted ventilation. Although the use of oxygen may improve the situation, the fundamental flaw is the perfusion deficit. Oxygen must be continuously delivered by the blood to the cells for normal cellular metabolism to occur. Carbon dioxide, a byproduct of aerobic metabolism, must be carried back to the lungs to be blown off in exhalation. A disturbance in this transport system may lead both to cellular hypoxia, a lack of oxygen available to the cells, and to hypercarbia, a buildup of carbon dioxide in the blood. Both hypoxia and hypercarbia pose problems for normal cellular function and stability. Both oxygen and carbon dioxide are transported to the blood, but in different ways. It's important to remember that oxygen and carbon dioxide move from areas of higher concentration to areas of lower concentration. This helps explain the movement of gas molecules between alveoli and capillaries, and between capillaries and their cells. Approximately 1,000 milliliters of oxygen is delivered to the cells every minute. Oxygen is transported by the blood in two ways. 1.5 to 3% of it is dissolved in plasma, and 97 to 98.5% of it is attached to hemoglobin molecules, which is then transported throughout the body. Hemoglobin is a protein molecule that has 4 iron sites for oxygen to bind to. Thus, one hemoglobin molecule could carry up to 4 oxygen molecules. Once an oxygen molecule binds with hemoglobin, it is referred to as a oxyhemoglobin. A hemoglobin molecule that has no oxygen attached is referred to as deoxyhemoglobin. Without hemoglobin, the negligible amount of oxygen that can be transported by plasma would not be enough to sustain normal cellular function or life. A loss of hemoglobin, which commonly occurs as a result of bleeding, can easily lead to severe cellular hypoxia, even though an adequate amount of oxygen is available within the alveoli. Carbon dioxide is transported in the blood in 3 ways. Approximately 7% is dissolved in plasma, 23% is attached to hemoglobin, and 70% is in the form of bicarbonate. The largest amount of CO2 diffuses from the cell into the blood and then into the red blood cells. In the red blood cell, CO2 combines with water to form carbonic acid, which then dissociates into hydrogen and bicarbonate. Bicarbonate then exits the red blood cells and is transported within our plasma. When blood reaches the lungs, bicarbonate diffuses back into red blood cells, where it combines with hydrogen and then dissociates into water and CO2. CO2 then diffuses from the blood into the alveoli and is released through exhalation. Gas molecules move from areas of high concentration to areas of low concentration. So O2 moves into the capillaries where oxygen content is very low, while at the same time CO2 moves in the opposite direction. One of the determinants of an adequate blood pressure and perfusion is blood volume. An adult has approximately 70 milliliters of blood for every kilogram, or 2.2 pounds, of body weight. Thus, a patient who weighs 154 pounds, or 70 kilograms, would have approximately 4,900 milliliters, or 4.9 liters of blood volume. Blood volume correlates with body mass. Therefore, a larger patient would normally have a greater blood volume. The loss of 1 liter of blood in a 100-pound patient would be much more significant than in a 200-pound patient. Question for y'all. Who here has ever attempted to or knows how to figure out how much you weigh in kilograms? Well, by me just saying that a kilogram is 2.2 pounds, that doesn't really help you very much. So I'm going to show you a quick and easy method to go from pounds to kilograms. So if you have, give me a second. There we go. Oh, forgive my handwriting. So if I have a 150-pound patient, okay, I am in pounds. What is it in kilograms? Well, the first thing you want to do is to get that 2.2 is divide 150 by 2, which equals 75. But you still got to get that 0.2, right? So what you're going to do, if you have a 2-digit number here when you're in your conversion, you're going to subtract by the first number. So you're going to take 75 minus 7, which then equals 68. Now, if you have someone that weighs, let's say, 300 pounds, 300 divided by 2 equals 150, right? Now, if, as I said, with a two-digit number, such as what we had in the 75, you would subtract by the first number. Well, in this case, I have a three-digit number. So in this number, I'm going to subtract by the first two numbers. So I'm subtracting 10%. So I'm going to take 150 minus 15. Equals 135. Make sense to everybody? Alright. Blood is composed of formed elements and plasma. The formed elements, which are cells, make up approximately 45% of blood composition. Plasma is the fluid component that accounts for the remaining 55%. Plasma is made up primarily of water and plasma proteins. Water comprises 91% of plasma. The plasma proteins consist of albumin, antibodies, and various clotting factors. The formed elements in the blood are red blood cells, white blood cells, and platelets. The red blood cells, which contain hemoglobin, are primarily responsible for carrying oxygen and delivering it to cells for metabolism. The white blood cells, or leukocytes, protect the body against infection and eliminate dead and injured cells and other debris. The platelets, or thrombocytes, are not actual cells, but fragments that play a major role in blood clotting and the control of bleeding. Blood is distributed throughout the cardiovascular system. The majority of blood is housed within the venous system, which is also known as a reservoir or capacitance system. The venous system can enlarge or reduce its capacity to respond to increases or decreases in the blood volume. The venous system is responsible for supplying the right side of the heart with an adequate volume of blood. If the volume entering the right side of the heart is decreased, the amount ejected from the left ventricle through the arteries and to the cells is also reduced. Thus, the venous volume plays a major role in maintaining blood pressure and adequate perfusion of the cells. So within, let me give my laser pointer, when you're looking at the blood, 64% of your blood is contained within the venous system, within your veins. 13% is contained within arteries, 9% within your pulmonary vessels, 7% within the capillaries, and 7% within the heart. Y'all bear with me, we're almost done, I promise. Hydrostatic pressure is the force inside the vessel or capillary bed generated by the contraction of the heart and the blood pressure. This pressure exerts a push inside the vessel or capillary. That is, it wants to push fluid out of the vessel or capillary through the vessel wall and into the interstitial space. A high hydrostatic pressure would force more fluid out of the vessel or capillary and promote edema, which is swelling from excess fluid outside the vessels. So imagine you have, if you will, a water hose. Okay? You have water flowing through the hose. Okay? All throughout the hose, you have sections. Let me extend my hose a little bit. Sections of it pushing on it in every microscopic spot. Well, what happens if you have a kink, or if thus the pressure beginning to increase? Right, the hydrostatic pressure increases because now there's a blockage, so all of this is beginning to build. To eventually, it's got to go somewhere, so it begins to push out of the cell. Plasma oncotic pressure. Plasma oncotic pressure, also known as colloid oncotic pressure or oncotic pressure, is responsible for keeping fluid inside the vessels. A force is generated inside these vessels by large plasma proteins, especially albumin, that attracts water and other fluids. Opposite to hydrostatic pressure, oncotic pressure exerts a pull inside the vessel. A high oncotic pressure would pull fluid from outside the vessel through the vessel wall and into the vessel, thus causing fluid to come in. So if I have a high hydrostatic pressure, so I have that clot here, fluid's coming out. But if I have a high oncotic pressure, or a decrease in hydrostatic pressure, is going to pull water into the capillary. To have an adequate blood volume and perfusion, to have an adequate blood pressure and perfusion, the myocardium must work effectively as a pump. The heart can vary its output to meet a wide range of physiological demands. It can drastically increase its pump function up to 6 times. The pump function is typically expressed as the cardiac output. Cardiac output is defined as the amount of blood ejected by the left ventricle in 1 minute. So heart rate times stroke volume. The heart rate is defined as the number of times the heart contracts in 1 minute. The heart has the property of automaticity, meaning it can generate its own impulse. The sympathetic and parasympathetic nervous system exerts control over the heart rate through the cardiovascular control center located within the brainstem. So an increase in stimulation by the sympathetic nervous system increases the heart rate, whereas a decrease in stimulation by the parasympathetic nervous system decreases the heart rate. So if you have a decrease in stimulation by the sympathetic nervous system, you would probably have an increase in stimulation by the parasympathetic nervous system, causing a decrease in the heart rate. And a decrease in stimulation by the parasympathetic nervous system causes an increase in the heart rate. Stroke volume is defined as the volume of blood ejected by the left ventricle with each contraction. Stroke volume is determined by preload, myocardial contractility, and afterload. Preload pressure is created by the blood volume in the left ventricle at the end of diastole, or at the end of relaxation. The available venous volume plays a major role in determining preload. So an increase in preload increases stroke volume, which increases the cardiac output. Contractility, which is based off the Frank-Starling law of the heart, states that as blood fills the left ventricle, it stretches the muscle fibers. So the stretch of the muscle fiber determines the force available to eject the blood from the ventricle. Afterload is the resistance in the aorta that must be overcome by contraction of the left ventricle to eject the blood. High diastolic blood pressure creates high afterload, which increases myocardial workload. Thus, over time, high afterload could lead to left ventricular failure. So some factors that could increase cardiac output would be an increased heart rate to a point, because eventually your heart rate's going to be so fast that it can't refill the heart efficiently. Lower diastolic blood pressure, beta 1 stimulation are all things that could potentially increase cardiac output. Factors that could decrease cardiac output would be such things as a drop in heart rate or blood volume, stimulation of the parasympathetic nervous system, or taking beta blockers that blocks the effects of beta 1. Systemic vascular resistance is the resistance that is offered to blood flow through a vessel. As a vessel constricts or decreases its diameter, resistance inside the vessel increases, which thus typically increases pressure inside the vessel. Conversely, as a vessel dilates, increasing its diameter, resistance inside the vessel decreases, which typically decreases pressure inside the vessel. Vasoconstriction is the term for a decrease in vessel diameter. Vasodilation is the term for an increase in vessel diameter. So vasoconstriction, decreased vessel size, increase in SVR. Vasodilation, I have a increased vessel size thus causing a decrease in the systemic vascular resistance. There we go. My computer's wanting to act up on me. The systolic blood pressure is a relative indicator of the cardiac output, whereas the diastolic blood pressure measures the systemic vascular resistance. If the systolic blood pressure is decreasing, it is an indication of a diminishing cardiac output. The pulse pressure is the difference between the systolic and the diastolic blood pressure readings. A narrow pulse pressure is defined as anything as a difference being less than 25% of the systolic blood pressure reading. Microcirculation is the flow of blood through the smallest blood vessels, the arterioles, capillaries, and venules. The true capillaries are the sites of exchange of nutrients, oxygen, carbon dioxide, glucose, waste products, and metabolic substances between the blood and the cells. Medarterioles are described often as thoroughfares or channels that connect the arterioles and venules. So as you have arteries coming in, it comes down into arterioles. You have precapillary sphincters, that way depending on any stresses that might be going on, they could shut off these sphincters to shut off blood, to shunt blood to the core areas. Okay, then it goes through the capillaries, goes through perfusion, then it comes back to the venules and back up into the veins, back to the heart. You can have some regulatory influences on these sphincters. Local factors such as temperature, acidosis, and histamines are the most influential. You can have neural factors that are the most immediate influence when disturbance arises that overwhelms the local factors, such as when the sympathetic nervous system and parasympathetic nervous system is activated. You can also have hormonal factors that provides prolonged vasoregulatory control of vasculature, such as epinephrine stimulating alpha-1 receptors, which causes precapillary sphincters to constrict. So your blood pressure is the sum of cardiac output times systemic vascular resistance. Thus, when it comes to systemic vascular resistance and the heart rate on cardiac output, an increase in SV causes an increase in cardiac output. Thus, a decrease in systemic vascular resistance causes a decrease in cardiac output. An increase in heart rate increases cardiac output, and a decrease in heart rate decreases cardiac output. That makes sense to everybody? Awesome. So the body's compensation mechanisms are geared toward maintaining pressure inside the vessel and perfusion of the cells. So when it comes to cardiac output and systemic vascular resistance on blood pressure, increasing cardiac output increases blood pressure. Just like increasing your systemic vascular resistance causes an increase in blood pressure. And decreasing cardiac output or decreasing systemic vascular resistance thus causes a decrease in blood pressure. Perfusion of cells is linked to your blood pressure. To maintain adequate perfusion, the blood must be pushed with enough force to constantly deliver oxygen and glucose to the cells and remove carbon dioxide and other waste products. The general effect of blood pressure on perfusion is an increase in blood pressure increases cellular perfusion, while a decrease in blood pressure decreases cellular perfusion. Baroreceptors are stretch-sensitive receptors located in the aortic arch and carotid sinuses that detect changes in blood pressure. As the pressure inside the vessels changes, it decreases or increases the stretch of the fibers of the baroreceptors. These baroreceptors, having detected the change in blood pressure, send impulses to the cardioregulatory center in the medulla of the brainstem to make compensatory alterations in the blood pressure. The cardioregulatory center increases the heart rate and force of myocardial contraction via the cardioexcitatory center by increasing sympathetic nervous system impulses to the heart and reducing parasympathetic nervous system impulses. As previously discussed, the chemoreceptors monitor the content of oxygen, carbon dioxide, hydrogen ions, and the pH of the blood. Stimulation from the chemoreceptors to change the cardiovascular system occurs only when there is a significant change in oxygen or carbon dioxide content or pH in arterial blood. So if you have a decrease in O2 and an increase in CO2 and hydrogen, that's what your peripheral chemoreceptors monitor and will react to. And with central chemoreceptors, if it notices an increase in CO2 or an increase in your pH, that's when you're going to get that respiratory rate or tidal volume increase. Alright, so just to review, there's 21% oxygen in the ambient air that we breathe in now. You want to make sure for aerobic metabolism to function properly that the airway is patent, that you are able to get air in and out properly. Minute ventilation is the sum of ventilatory rate times tidal volume. Be sure to look over what alveolar ventilation is. Let's see. Also, look over ways how our care can influence these processes. Whether it is finding ways to reduce pressure or to stop bleeding or provide ventilations. Look over the various vital signs for a patient so that we have an idea of what a normal heart rate is. Okay? Look over, make sure you review what the determinants of your cardiac output, your systemic vascular resistance, and what stimulates the sympathetic and parasympathetic nervous system as well. Excuse me. Alright guys, so that's it for today. Once again, I'm sorry that this chapter went a little bit long, but at a certain point I was like, I'm right here at the end. I promise I'm going to try to keep these videos down to about 20 to 30 minutes. If y'all have any questions, please shoot me an email. I'll try to get them back to you as soon as I can. And other than that, I will see y'all in class. Bye.